In this video, we will be talking about the four principal quantum numbers and the Schrödinger wave equation, which will enable us to describe what the orbitals of electrons in atoms look like. As described previously, the Bohr model of an atom in which electrons are traveling around the nucleus in planetary-like motion has some issues with it. These issues include if the electron is traveling around in a circular planetary-like motion, then it would be generating an electric field perpendicular to the direction of motion. This would violate the first law of thermodynamics, in which energy can neither be created nor destroyed. Another issue with the Bohr model is if you have electrons that are traveling in ordered circular paths, then it would have a determinant motion to it, which would violate the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that there is a certain minimum amount of uncertainty in both the position and the momentum of matter. In the Bohr model, if you have an atom traveling in a set path, then you could know both its momentum and its location at any given point in time. Instead, what we now have is a probabilistic or an indeterminate description of the position of electrons, which is given by the Schrödinger wave equation. The Schrödinger equation allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location in the atom. The Schrödinger wave equation uses differential equations in order to determine the energy of a particular wave function. The wave function itself is this psi here, a symbol that looks somewhat like a trident. Essentially, you have a function that's operating on the wave equation, which returns an energy times that same wave equation. Because this uses differential equations, we will not be going into that depth of information in this course. However, it is important to know that there is such a thing as a wave equation. The solution to Schrödinger's equation produce many different wave functions, and it is a plot of distance versus the square of the wave equation that represents the orbital shapes that we'll be talking about in subsequent videos. These orbitals are a probability distribution map of the region where the electron is likely to be found. Essentially, these equations themselves have a couple variables that get plugged into them, which are what we know as our quantum numbers, which will dictate the shape of the orbitals where we can find the electrons. The calculations that involve the Schrödinger wave equation that show the size, shape, and orientation in space of an orbital are determined to be three integer terms in the wave function. These integers that allow us to come up with the solutions for the wave equation are called the quantum numbers. There are four quantum numbers. There is the principal quantum number, which we will label n, which dictates the particular energy level for all the orbitals in it. There is the angular momentum quantum number, which is represented by an L, which describes the type of orbital in which we will find the electron. There is the magnetic quantum number, the m sub L, which tells us the position of the orbital in an XYZ plot. And then the last one is the spin quantum number, which will be labeled as m sub S, which tells us the orientation of the spin of the electron. The first of the quantum numbers is called the principal quantum number, and again is given a symbol n. It characterizes the energy of the electron in a particular orbital. It is what we were using in Bohr's model to describe the different energy levels. Values of n can be any whole number integer, 1 or greater. The principal quantum number will determine the size and energy of an orbital. The larger the value of n, the more energy the orbital has, and the larger the value of n, the larger the orbital will be. Energies are defined as being negative and are relative to the amount of energy that it takes to fully remove the electron from the atom. An electron's energy is lowered, i.e. made more negative, as a result of its interaction with the nucleus of the atom. An energy would have zero energy if it escapes from the atom. As n gets larger, we have the following that occurs. The amount of energy between the orbitals gets smaller, and the energy of the orbital becomes greater, i.e. less negative. The next of our quantum numbers is the angular momentum quantum number, which is represented with an L value. The angular momentum quantum number, or L, determines the shape of the orbital. L can have integer values starting at 0 and going to n minus 1, where n is our principal quantum number. So you will first determine what your principal quantum number is, and then you will determine the angular momentum quantum number. Each L value is designated by a particular letter that tells us what the shape of the orbital will be. An L value of 0, we will use a designation of S. An L value of 1, we will call p orbitals. An L value of 2, we will call d orbitals. And an L value of 3, we will call f orbitals. Again, the L value, the angular momentum quantum number, is what tells us the type or shape of the orbital. The next quantum number is the magnetic quantum number, m sub L. It tells us the direction in space that the orbital is aligned relative to the other orbitals. The values that are possible for m sub L depend on the L value. So to determine your m sub L, you first have to know your principal quantum number n. That n value will dictate what the possible L values are, and those L values will tell us what possible m sub L values we can work with. So the value of the integers for m sub L range from negative L to positive L and will include 0. This will give us the total number of orbitals for a particular shape. So let's say you have your angular quantum number, L, equal to 2. The value of m sub L could be negative 2, negative 1, 0, plus 1, or plus 2. This tells us that there are 5 different orbitals for the L equal 2, and L again would be our d-type orbitals. The last of the quantum numbers is the spin quantum number, m sub s. The spin quantum number describes the spin behavior, also known as the angular momentum, of an electron in an atomic orbital. It specifies the orientation of the electron in the orbital. All electron spins are equal in magnitude, but differ only by the orientation. There are 2 possible values for the m sub s. M sub s can either be plus 1/2, which we will call spin up, or minus 1/2, which we will call spin down. One of the things that we are interested in is what different sets of 4 quantum numbers are possible for a given electron. So we're going to look at a problem to try to determine what are the possible quantum numbers if we start out with a principal quantum number of n equals 2. So just to review, our n values can be integer values starting at 1. So n could be 1, 2, 3. Could be any integer value, technically up till infinity. Then we have our L values, which can range from 0 by integer values up till our value of n minus 1. Then we can have our m sub L values, which can have values of negative L through, including 0, up till positive L. And then our last one, m sub s, can either be plus 1/2 or minus 1/2. So let's say that we have an n equals 2. And we're going to write this out as a flowchart to look at all the different possible sets of quantum numbers that can start with an n equals 2. So if n equals 2, then we could have an L value of either 0 or n minus 1 would be 2 minus 1 is 1. So we could have a value of either 0 or 1. If L is equal to 0, then there's only one possible m sub L value, and that would be 0. If L is equal to 1, then we could have three possible m sub L values. M sub L could either be negative 1, it could be 0, or it could be positive 1. Last, we look at the m sub S values. Each m sub L can be split into two possible m sub S values, plus 1/2 and minus 1/2. So what this tells us is that for the n equals 2 principal quantum number, there are two different paths that we could take. We could be looking at the L equals 0, which are our s orbitals. There is only one orientation for an s orbital, which is the m sub L equals 0 orientation, and there are two different values for spin that can go in the s orbital. If n is equal to 2, we could also have L equals 1, which are our p orbitals. Our p orbitals can have three different values, which means we have three different p orbitals in different orientations. One orientation is described by the m sub L equals negative 1. One orientation is the m sub L equals 0, and another orientation is the m sub L equal plus 1. In each one of those orientations, there are two different locations that we can put electrons, one having an electron spin up and one having an electron spin down. So what this tells us is that in the n equals 2, shell, we can have a total of 4 different orbitals holding a total of 8 different electrons. Each set of the first 3 quantum numbers describes a particular orbital. The m sub S describes the electrons that we are putting into the orbitals. The orbitals with the same n value are said to be in the same principal energy level, also called the principal shell. Orbitals with the same values for n and L are said to be in the same sublevel, also called the same subshell. There are a bunch of different ways of illustrating the energy levels and sublevels. Going back to our example of n is equal to 2 for the principal energy, it will contain two sublevels. So this particular diagram here is showing the n is equal to 3 principal level, n is equal to 2 principal level, and n is equal to 1 principal level. So the one we did in our problem was this one here, the n is equal to 2. For the n is equal to 2, there are 4 different orbitals, which are represented by these small little boxes, which later on we will be putting up and down arrows to denote the different m sub S values. So we could have our n is equal to 2, L is equal to 0, which would be our 2s orbitals. And because the m sub L value ranges from negative L to positive L, if L is equal to 0, then there can only be one value for m sub L. So for the s orbitals, there's only one orbital. For the cases where L is equal to 1, there are 3 possible values for m sub L, negative 1, 0, and 1. So for the p orbitals, which is another way of talking about the L is equal to 1, right? If L is equal to 1, then we call those the p orbitals. There are 3 possible p orbitals, one in which m sub L is equal to negative 1, one for m sub L equals 0, and one for m sub L is equal to plus 1. We will later be using these types of diagrams to predict different types of behavior of atoms in both electric fields and later on how they will bond to other atoms.